histogram, and how the histogram can be used to represent an image, and what information we get about the contrast of an image. And then we saw about the spatial filters, different types of filters. We saw the example of a box filter, that's an averaging filter, and we also saw the Gaussian filters, how the Gaussian filters can be used for the smoothing operation of an image. And we looked at the concept of convolution, right? And then we also saw sharpening spatial filters. We looked at the first order derivative as well as the second order derivative operators, basically the gradient edge operators, the Previtt-Sobel operator, as well as the Laplacian operator, and we also saw some examples. And in the previous lecture class, we had seen certain the concept of frequency, about the Fourier transform, and the different filters in the Fourier domain, that is how the low pass filter, high pass filter, and band reject filters help with processing an image to get details of either the edge or with the smoothing operation, or to remove the noise. That is for different applications. And we also saw the concept of sampling and aliasing, and about Gaussian pyramid, right? So in today's class, what we'll be discussing about is the image features, or how we can represent the images. Is my PPT visible to all?
Yes, ma'am.
Yes, ma'am.
Okay, okay. Now, image representation. In images, if you look at this image at the top left corner, right? This particular image, we see that there's a lot of information in that. Okay, it's basically the an infrared image, and the region of interest for us is this particular canal, right, like region that we see over here. Okay, so in some of the images that is being captured now, there are different reasons for which we use the images. Some may be for segmentation and finding what is the shape of the particular object of interest, or maybe it is to find the texture of the particular object in order to recognize what type of object it is, or to classify it into a particular class of an object. Okay, or sometimes it is just to identify what is the route, or what is the directional information, or so. Okay, so there are various purposes with which we process the images. Now the image that we have, that is the image that we have directly captured, may have a lot of information which is not exactly useful for us. Okay, now for example, in this particular image, what I am concerned with is about this particular black region, or this particular canal like thing that you see over here. That is a region of interest for me, or the object of interest for me. Okay, and all the other details which I find in the surroundings or in the background is not useful for me, or I do not need it. Okay, so when I work with such images where there are high details of regions which is not of interest for me, it may be easier or more convenient for me to process, or represent this particular image in a form where it contains only useful information which is useful for me for further processing, rather than taking all the information which is present in the image. Or just putting it in another words, what I'm trying to say is, instead of having all the details of each and every pixel intensities which are present in the image in regions where it is not really relevant for me, or which is not really useful for me, I need not process all these intensity variations when I'm working further, right? So in such cases, I can discard these information, and I can try to represent the image in a form where I have only the useful information which I need. Okay, and again, when you have when you're considering all the pixel intensities, like for example, what we discussed last class was, in the images you have pixels, and depending upon what bit image it is, that is whether it's an 8-bit image or a 16-bit image or so on, the number of pixel intensity levels in an image that it can have, the dynamic range would increase depending upon the value of k, or the increase in the value of k in a k-bit image, right? So as the pixel intensity levels also increases, okay, you will need more, what is it, the size by which you have to store the particular values of the image, okay, that also increases, right? Now you may not need to store all the pixel intensity values, okay? So in such cases, these image representations, or trying to represent an image in a form where you need not consider all the pixel intensity values present in the image, okay, is what we are going to discuss in this particular lecture class, okay? Now in this example, what has been done is, this is just an example, what has been done is an image has been taken, right? Now in this image it has been thresholded. Now thresholding is an operation where you try to convert a given image into a binary image where you have zeros and ones. That means you kind of what to say, you assign a threshold value, that is a cutoff value, okay, and you say that all pixel intensities which are below this particular cutoff is given a 0 or a 1, okay, and the pixel intensities which are above this cutoff value is given a 0 or 1, and so on. So like that you get a thresholded image. So this is one thresholded image which has been obtained from this image. Now after thresholding this image, the connected component analysis is done, which means that an algorithm is used to find out which is the object, okay, which is the largest connected component which is present. So as we see here, this particular region is the largest connected component, and that has been extracted, okay. And then by using a skeletal operation, or finding the skeleton of the image, okay, that means you're just trying to reduce the thickness of this to 1 pixel intensity value, so you'll get an image which looks somewhat like this, okay. So now if you compare this particular image with this initial image, what you see is you have all the details with regard to the shape as well as the direction of this particular image being represented by this. So I can say this image is another representation of this particular image, and the advantage I have with this particular image is that all the information in the background which I do not require is no longer present over here, right? And I also have information, all the information about the the route or the direction, okay, as well as the shape of this particular object over here, okay. And since it is a single pixel thickness over here, okay, again the number of levels to which, or the feature dimension, okay, is reduced over here. I do not need many values in order to represent this particular image. Now since it is a binary image, this has been obtained from a binary image, the only intensity values I have is 0 over here and 1 over here, right? So this is just one example how representing an image in another form can help us with further processing, or better representing the image. Now, there are various other ways by which you can represent an image, or you can extract useful information from an image, and these are some examples. Over here, what you see is from this building, okay, you're finding key points. This is an example of finding key points. Now, what key points means is you're trying to find points in an image which would help to represent that particular image in a better way, but at the same time it retains all the information regarding the corners, okay, the edges, or the direction or to which the edges point to, or the corners point to. All these information is present within the key points, but at the same time you need not store all the values over here, right? It is just the key points, the location of the key points, the direction of the gradients, etc. Only needs to be stored. So this is one representation of an example of how you can represent an image using key points. Now here what you see is another form of representation where you can transform the given images. Now in these cases the given images is in the form of 0 1 2 and so on. You can assume these as images, and these images can be transformed to you can use a particular transform, any transform, it can be any kind of transform. You can use it to represent it in a feature space. Okay, so basically extracting features from images is another way by which you can represent images. Now a third way by which you can represent images or you can extract useful information from images is by looking at the texture of the objects which are present in the image. Like for example, this is an object, okay, in which there is no specific texture. Okay, and here this it is the same object with a particular texture. So just to show you what texture exactly means. So texture means you can make out a certain kind of pattern which is present in an object. Okay, and that kind of pattern would be maybe different from the background in which the object is present, or it may be different from other types of objects that you are trying to classify. If you are trying to classify between two different kinds of objects and these two objects have two different texture regions or texture variations, okay, then these kind of methods where it can help to represent only the texture information which is present in an image would help with classifying such kind of objects. Okay, so these are just a few examples by which you can represent an image in another form. It could be a transform, it could be in the form of key points or in the form of texture descriptions. So we'll just have a look at one example of each of these techniques. First, we will be looking at histogram of oriented gradients. Okay, it is called as HOG, histogram of oriented gradients. So just as the name says, what we do is we find the gradient of an image first, right? And we look at the orientations which are present in the gradients. And depending on those orientations, we make a histogram of the orientations. Right, so usually when I say histogram, or in the first class when we discussed about histogram, we discussed that basically what you do is you look at the pixel intensity values and then you try to categorize them into different bins, okay, depending upon what exactly is the pixel intensity value, and that is what you call as an image histogram. In this case, instead of considering pixel intensity values, what you consider is the gradient orientation. So you look at the orientation of the gradients and then try to categorize that into different bins. And so it's a different method of how you calculate the histogram. In this case, we'll see that in detail. Okay, so HOG feature extraction, it is one of the most popular feature extraction techniques which are used in image processing applications. Okay, and as I said earlier, what we do is we calculate the gradient. So as we discussed in the last class, when you see gradient, it is a vector quantity, so it has got a magnitude as well as orientation. And here what we do is we take the orientation information in order to determine or compute the histogram, right? Now it is a global descriptor. So what we do is we kind of look at different patches, and then depending upon image patches, we will look at the gradient. We compute the gradient and then take the histogram of that. Okay. Now I'll just describe this in detail. So if you look at this image over here, okay, you see that it's an image of a person walking, right? And you have a background where it looks like it's a homogeneous intensity in the background over here, and there is something like a bridge or a path over here, right? Now, histogram of gradient operator, okay, or HOG feature extraction. Initially, it was introduced, or it was developed by a research team in order to detect the presence of a person in an image. That was initially why it was developed, or how it was developed. Later, it had been used for detection of various kind of other objects. Also, it has been extended to various other applications. Here we'll just look at some examples where we consider images of a person and see how HOG helps, or the orientations will help to identify the presence of a person in an image. So here, this is the image. This is an example of an image where there is a person present. Now, how we calculate HOG here is we take different blocks over here. Okay, so and for each block we are calculating or computing the gradients, right? And for each block that we are considering, right, there must be an overlap between the adjacent blocks. Okay, and we take a 50% overlap. So for example, if I'm taking a 2 cross 2 block, it would look somewhat like this, where you have 50% overlap between the adjacent blocks, right? Now, once you consider each of these blocks, what we do is we try to calculate the gradient orientation as well as the magnitude. Both the information is obtained with calculating the gradient, right? So what we do is, after finding the gradient, we look at the orientation, and we divide that or quantize that into 9 bins. Now, that is one difference from how an actual histogram is being calculated. When you actually try to calculate the histogram of an image, like how we discussed in the previous class, you will get a histogram with the number of bins equal to the number of intensity levels which are present in an image. Like for example, if it is an 8-bit image, okay, in an 8-bit image, the number of intensity levels which are present is 256, right? So if you're taking the histogram of such an image, an 8-bit image, the number of bins which are present in the histogram is also 256, because you're trying to calculate, or you're trying to see the intensity value of each and every pixel, and then try to put it into the bin of the corresponding intensity value, right? In this case, what you're doing is you're not looking at all the gradient orientations, or you're not trying to put all 180 bins. Like if you're looking at the gradient orientations is 0 to 180, you're not trying to put it into all 180 bins. Instead, you are creating a histogram with only 9 bins. Okay, and these 9 bins will help to categorize, or will help to what collect the orientation information from 0 to 180. Now, how that is done is, to calculate or to put it into 9 bins, you're taking increments of 20 degree orientations. Okay, so the first bin which I have here would have a value ranging from 0 to 20. The next would be from 20 to 40. Next would be from 40 to 60, and so on. Okay, and finally you have here from 160 to 180, and therefore you'll have in total 9 bins. And these which you show here, 10, 30, 50, those are the centers of each bin. So since I have from 0 to 20 for the first bin, the center of that is 10, right? Here from 20 to 40, so the center is 30, and so on. Now, into these 9 bins, we will put these gradient orientations depending upon what is the orientation value. Okay, so that is one point you have to remember. Now, the sign of the gradient is ignored. That is why you have only from 0 to 180. Now, another point over here is that we do not add +1, or you do not completely categorize, or you do not completely put the orientation values in a particular bin if it is ranging from 0 to 20, as you do in the normal histograms. What I mean is, when you're calculating the normal histogram of an image, okay, let's say it's an 8-bit image, so you have 256 values and 256 bins. So if I have a pixel, the pixel which I'm considering, if the value of that is 100, what I do is to the bin in the histogram which has a value 100, I will put that particular pixel value. Now again, if the next pixel value is also 100, what I do is again I put that into that bin. So now I have 2, the value 2. So this particular frequency or the number of pixels which I have in that histogram will be 2. Again, the next time when I again encounter, or when I again come across a pixel with a value or intensity value 100, again a plus 1 is added to that particular bin. So I have now the value in that particular bin is 3, right? And so on. But in this case, the way how you add to the each of these bins is a little different. You're not doing a plus one. Instead, you look at how far the particular value or the orientation value we are considering is from the center of the bins, and accordingly we kind of divide that and distribute that along the different bins. Like for example, if I am having a value, theta value, that is the gradient orientation value of 85 degree, right? So if I look at the bins over here, I have the centers 70 and I have the center 90, but I do not have a value 85, right? So what I do is 85, it is more closer to the center 90, right? So that means more of this or more weightage of this is given to this particular bin with the bin center 90, and less weightage is given to the bin the one with the bin center 70. Okay, so I have this particular value, or a 3 by 4 is added over here and a 1 by 4 is added over this particular bin. Okay, so I am basically distributing this orientation value depending upon, or according to how much distant it is from the bin centers. Okay, so like that. Now if I'm having if the value which I'm having is, let's say, 50, if I get 50, then that is equal to the exact bin center 50. So then it will be a plus 1 is added over here. Okay, there is nothing added to the neighboring bins. Okay, it comes directly because it exactly coincides with the bin center. If it is deviating from the bin center, then accordingly the values will be distributed across the neighboring bins. So by doing this, what we achieve is we are trying to interpolate the values between the different bins over here. Okay, so like that we calculate what is the histogram, right? And this is what you call as the histogram of oriented gradients, where you calculate the gradient, you find the orientation, and then create the histogram this way using the gradient operations rather orientations, rather than taking the pixel values as we do in the normal histogram. Okay, so now what I have is, now this is for a block, right? Now this one you're doing for one block, for each block, right? So that means every block will have its own particular histogram, right? Or HOG, histogram of oriented gradient would be there for each and every block. And now what you do is you concatenate all these histograms together, okay, as a feature vector, and that would give me the final HOG. So this would, after concatenating all the histograms, what you get is called as the histogram of oriented gradient feature. Okay, so this would be my HOG feature. Now, if I try to visualize the HOG for an image, it would look somewhat like this. That is, this was the image which was shown earlier of a person who is walking along a particular lane or a small path over here, right? So if I calculate the HOG, you can easily identify that these background regions where there is a uniform uniform intensity variations, okay, there you'll see that here also the orientations that would be present would also be somewhat uniform, right? And in these regions also you see that it is kind of uniform. But in the region where the person is present, okay, you'll see that the orientation differs. So you can kind of imagine that you have a person here, so you have the body here and the hands over here, the legs here, and so on, right? So if you look at this particular hand region, you see that the orientation also points to that particular region, right? And another example is here also you see there is an image of a person who is standing with arms wide apart, and so in the histogram of oriented gradient image, HOG image, also you'll see the presence of, you know, these hands over here, the legs over here, whereas the what background region, okay, in the background region you see that it is of uniform orientations, okay. Now, so the advantage of using the HOG is that when you have the presence of a person who is walking or running or etc. in a particular image, it becomes easier to identify the person by looking at just the image. And as I said, this has been applied for various other applications also. It need not be a person alone. And by looking at this particular image, it is actually another form of representation of this you know, original image, where you do not take any intensities into consideration but just the orientation of the gradients alone to detect the presence of a particular object of interest, okay. And that is how the HOG features help. Okay, do you have any doubts so far? Okay, then I'll move on to the next topic. Now, another feature descriptor as well as detector that we are going to learn is the Sift operator. Sift stands for Scale Invariant Feature Transform. So before we go to the details of Sift, okay, let's discuss what is a Laplacian of Gaussian operator. Okay. Now, just as the name says, what you do is first apply a Gaussian operator and then take the Laplacian of that to give the Laplacian of Gaussian operator, and this is abbreviated as LOG, okay, Laplacian of Gaussian, LOG. Now, when you're taking the Gaussian distribution and taking the Laplacian of the Gaussian distribution, what you get would be looking somewhat like this. Okay, so in this particular image, what we see is if we start from here, okay, there is a minimum, okay, and then this gradually increases. Now, as it increases, as it reaches the top, and there is a small decrease in the level, okay, and then it plateaus out or it flattens out, okay. So now this can also be called as an inverted Mexican hat, okay, because Mexican hat is a very popular distribution that you see, and this is an inverted form of that, okay. And just note that here, as it comes towards the top, okay, it does not flatten at the top exactly. It will have a dip. It kind of reduces at the top and then flattens out, okay. And this is a kind of structure that you will get, and this is basically the LOG operator, the 3D view of the distribution. Now, from this 3D view, I can create a 2D view where the various intensity values represent what is the height or the depth of each of these values. So here, this is the corresponding 2D representation. Here what we see is this particular minima is represented as the center over here, okay, and it is given a black pixel value or black intensity value because it is you know, the minima which is present in the whole distribution, right? Now from there gradually the value increases, it keeps on increases, right? And at the top you'll see that it will get the maximum value. So at this particular top, at this particular circular boundary, you have the maximum value, and then after that it reduces, okay, it dips or reduces and then flattens out, right? So it is reducing and flattening out, and that is why you have gray values around this, okay, because this is more this is like a projection that you have here, right? So this dips and then you have this value. Now this is the 2D representation of the log operator, and how you can represent over here is you can just use the formula del square g, because it's a Laplacian operator. It would be a second order, you're finding the second order derivative, right? And here dou square g by dou x square, so it would be in the x and y directions, but here g would represent the Gaussian, okay, rather than the image. Now, using the log operator, why it's important is we can find out, or it helps with blob detection. Blob means it's just a circular region, and blob detection means, let's say in an image you have certain blobs or blob-like structures, okay, round structures or circular structures which are present in an image, and log operators would help to find the presence of such blob-like structures which are present in an image, okay, and we will look at an example also next. Now another concept which before we go further is we can use these log operators as a mask, okay, while you are trying to do a convolution operation. Now as we see, the Laplacian of Gaussian operator is symmetric, right? Here if you look at this particular image, you see that it is symmetric along the x direction as well as the y direction, right? So when we do a convolution operation with a symmetric kernel, okay, it is equivalent to doing a correlation, or it is equivalent to finding out or trying to match a particular pattern which is present in the mask or the kernel, okay, with that of the image. That is, let's say you have a particular image and you want to find out the presence of certain patterns which are present in that particular image, then we can create a mask, okay, with that particular image or pattern that we are trying to find out, and you can call it a template. Now you can do a template matching across the image, okay, so basically that is a convolution operation with the symmetric mask, okay, and those regions where it perfectly matches with that of the image, where the mask matches with that of the image, will give you a high correlation value. And here also it's an example. Okay, and one more thing is, since you have a Gaussian operation over here, okay, there is one parameter in the Gaussian operation which you can control, or basically you can control the value of sigma in the Gaussian operation to get a blob size of our choice. So as we vary the value of sigma which is present in the Gaussian operator, you'll see that the blob, the size of the blob or the diameter of the blob also increases, okay. Now if you look at this particular graph, what we see is I have different images, and let's say in image 1 I have a small blob like structure. In image 2 I have a slightly larger blob, and image 3 I have a very large blob like structure. And if I consider log operators of different scales, I can create log operators of different scales by varying the value of sigma. So if I take a small value of sigma, I have this operator, and by increasing the value of sigma, I get larger blobs. Okay. Now, when I use these log operators, okay, these different log operators on when I convolve that with the images, what I get would be somewhat like this. That means, okay, let me consider image 1. When I'm trying to use this particular operator, okay, this does not perfectly match with the blob size over here, so I do not get a high value, but it matches with this particular blob size or the blob diameter, right? And so I get a high correlation value, and these are too big, these blobs are too big in order to match with this one, so I do not get a high correlation here, okay. So I get a correlation over here, which means that now this particular blob size matches with this blob log operator with the same blob diameter. Now, if I take a slightly larger image, okay, I'll see a higher correlation with an LOG operator having a larger sigma value. If I take a much larger bob-like structure present in an image, it will show a high correlation with an LOG operator with a much larger sigma value. So by varying the sigma values in the LOG operator, I'll be able to find different blob-like structures with of different sizes present in an image. It can be one particular image with different blob sizes or different images also. And we'll see one example of what this means. Okay, this is just an example of how in one particular image, if you are having different sizes of blobs. Now in this case, it is the patterns which are present in the wings of a butterfly. You'll see that accordingly you'll also see certain blobs of different sizes here too. Okay, so just to explain further what I was saying in the previous slide. So let's say I'm considering this image. This is an image of a sunflower field. So the sunflowers which are much closer to the camera are larger in size, and you have sunflowers which are further away. The blob size decreases, right, as the distance here. So this is an example of an image where you have objects of different blob sizes. Okay. Now, when I'm working on this with an LOG operator, what I do is I can vary the sigma size, okay, and convolve with this particular image and find out the output responses. So the output responses will be the correlation value. So depending upon how strong the correlation value is, I have more intensity values, and that is represented in the form of heat maps. So wherever I have a red color, that means that it shows a high correlation. So let's say sigma 1 is a large size, okay, large blob size of the Laplacian LOG detector. And when I'm convolving with this, here in this particular image, okay, so I see that the LOG operator has the same diameter as the blob in this particular sunflower, okay, and so I get a high intensity value in the output response. Okay, it shows the red color over here. Okay, and all sunflowers or all objects which have exactly the same diameter of the blob size as which is shown or represented by LOG operated with sigma 1 will have a high value. And what we observe is, even though there are blob like structures in the background over here further away, even though they are blob like structures, since they are smaller in size, that is not being detected here, right? So at the scale, you call this as scale, at the scale sigma 1, which is a high value, you'll see that all larger blob like structures are detected. Now when I'm decreasing the value of sigma here, okay, I get sigma 2. What happens is, now it's a smaller blob size. So blob-like structures with a smaller radius would be detected in this case. Okay, so some which are present over here have been detected. And like that, when I keep on reducing the value of sigma, okay, the corresponding blobs, okay, of those corresponding diameter would get detected. So what I see here is, now in this image you'll see that in sigma 4 that here the blobs have been detected. So this one you can see is corresponds to this particular set of sunflowers, and sigma 5 is able to detect the sunflowers which is even much further away from the nearest ones. Okay, that is, you can see over here that there are high intensity values. So what you're doing is you're basically trying to represent the LOG operator in different scales, and for each scale you're trying to convolve with the original image and trying to find out the blob, you're trying to detect the blobs for different scales, right? Now after that, what you do is, in order to find a key point, now what Sift is used for is, you have a Sift detector, okay, as well as a Sift descriptor. Now we are first discussing about Sift detector here. So what Sift detector does is, it detects key points in an image, right? So to find the key points, now you have all these image responses from different scales. Okay, what it tries to see is, let's say I have a particular point of interest, and let's say this particular point is my point of interest. Okay, and to find the key point, what I do is I just look at the neighborhood of this particular center point. Okay, so let's say it's a 3 cross 3 neighborhood. I consider the same neighborhood for the same location for the above scale, as well as the same location for the below scale, right? So that is the same of the same representation is shown over here. So let's say this is the center pixel which is under consideration. I take a 3 cross 3 neighborhood over here. Okay, I also consider the same neighborhood in the above scale as well as the scale below in the output responses. Okay, so now I have center pixel along with 26 neighborhood points. Okay, 26, because you have 9 pixels into 3. Okay, so that would be 27, and one of which 27 includes the center pixel itself, right? So if I look at the neighborhood, it is 26 neighborhood points, and totally it is 27 points. Now, once I have the neighborhood information, I try to calculate what is the extrema in this particular 26 neighbor points. Okay, so extrema means it could be either the maxima or the minima, right? And if the center pixel under consideration which I have, if it is equal to either the maxima or the minima among the 27 points in total, then it is considered as an interest point. Okay, I'll just repeat once again. What we are trying to do is we are trying to find out interest points from this image. When I say interest points, as I said before, we are trying to represent a particular image in the form of certain interest points within the image that can better represent the image, but with lesser dimensions, or lesser I would say lesser not information. The information is there, but lesser dimensions, or with lesser variables that is required. Okay, but still containing all the important information that we are looking for in the particular image. Now, to do that, we can find out interest points in the image, and Sift Detector is one such method where you can find the interest point. So let's say this is 1 center pixel. Now, accordingly, what you have to do is, now this is just as an example, we have taken this center pixel. You do that for the all the pixels which are present in the image. Okay, so let's say this is one, or any one particular center pixel has been considered. Now, once you have that center pixel, in order to find out whether that pixel under consideration belongs to, or it can be considered as an interest point, or interest point means whether it's a point of interest for us or not. To see that, what you can do is you look at the neighborhood of this center pixel, and you also look at the neighborhood with respect to the previous scale as well as the subsequent scale. And after considering all the neighborhood pixels, or not pixels, neighborhood points, we calculate the maxima or minima and see whether the center point which is under consideration is the maxima or minima. If it is the maxima or minima, then it is considered as an interest point. If it is not, then it is not taken as a interest point, and we go to the next center point. We take the next point and see whether that is an interest point, and so on. So we look at the whole image and try to identify all points of interest for us, right? Now, once we identify a particular point of interest, okay, then that interest point is saved, or it is noted down or saved in the form of x, y, and sigma. So here x and y determines what is the location of that particular center point, and sigma represents what is the particular scale it belongs to. Okay, so that is the x, y, sigma representation, and these interest points are saved in this form, x, y, sigma. So what we see here is Now, irrespective of what is the size of the blobs which are present in an image, by varying the log operator in different scales, we are able to identify blob-like structures. Okay, and we are able to detect the interest points now would lie in those regions where you have the blobs, right? So these key interest points are located and or detected and saved in the form of x, y, and sigma. So it is what it is robust, or you can say it is invariant to position as well as scale. So that is why we call it as a scale invariant interest point, because it does not depend upon, even if the scale changes or the size of the blobs changes in an image, it will still, the log operator would still be able to detect the presence of the blob like structures. Okay, and then a list of x, y, and sigma is obtained after this particular stage. Okay, so we have a list of interest points in the form of x, y, and sigma. As before. Now what you do is, along with this x, y, and sigma, we also calculate the orientation, which we'll see over here. Okay, so what we do is, now we have x, y, and sigma, and as I said, while by varying the size of sigma, larger value of sigma represents, or it detects larger blobs, and smaller value of sigma would represent smaller blobs, right? And because we are able to vary the value of sigma, we are able to detect different blob sizes, or you can say it is invariant to size, or the the size or the scale of the particular blobs which are present, right? Now in x, y, and sigma, what you have is basically the interest points which are present. Okay, now this particular operation, okay, is called as Sift Detector. Now what I'm going to discuss next is Sift Descriptor, which is different. Try to understand that there are two parts for this Sift feature extraction method, or the Sift method. So the first part was the Sift Detector. In the detector, what you're doing is, the only thing you're trying to do is detect a particular interest point or key point which is present, right? Now, as I said, after finding x, y, and sigma, what you do is, at that particular interest points, we also find out what is the gradient operation. Okay, so after finding the gradient, you try to find which is the best orientation along that particular key point or along that particular interest point. So I'll just take the next slide. Okay, so no, not this. Okay, yeah. So what you see here is along with the value of x, y, and sigma, okay, this is supposed to be sigma, you also calculate a value which is called as theta. Theta represents what is the orientation of the particular interest point. So what you do is, once the interest points are calculated or are detected, you find what is the gradient of that particular interest point, and find out what is the best orientation on the neighborhood over there, okay, or the dominant orientation at that particular interest point with respect to the neighborhood, and that would give me the value of theta. So the Sift key points are basically represented by xy, sigma, which is the scale, as well as theta, which is the gradient operation. Okay, and once Sift key points are detected, the next stage is basically the descriptor. Now detector simply detects what is the key point of a certain in a particular image, and descriptor, what it does is, it describes what is the particular region in which the key point is present. So if we see over here x, y, sigma, and theta, it does not tell anything about how the neighborhood is like. Okay, all it does is, it will say what is the position, what is the scale or the blob size, and what is the orientation. And in descriptive, what it does is, it will try to describe what is the neighborhood of that particular key point, and we'll discuss that further in this particular slide. Now, in a Sift descriptor, once the key points are identified, okay, so before there's if there's any doubt till now, I'll take that and then I'll move forward. Do you have any doubts till the Sift detector? Okay. Okay, one more thing you have to remember is the Sift detector and descriptor, as I said, it is two different stages. Once the key points are detected, you go to the descriptor, right? Now, the Sift detector and descriptor, they need not be always they are mutually independent or exclusive, so which means that I can use a Sift detector, okay, and maybe use some other kind of descriptor. It need not be followed by the Sift descriptor alone, or I can use some other detectors to find the key points and then use the Sift descriptor. Okay, so it's not that you have to use only Sift detector and descriptor alone. Like for example, there are different other methods also for you to find, or that helps you find the key points. Sift is one of the most popular techniques which have been used for finding key points. There are other methods also, like for example surf and brisk, which are also popular methods to find the key points in a particular image. So there also you can combine different kinds of detectors with the Sift descriptor, or vice versa. So basically the objective or the aim of the Sift detector is to simply find key point locations in a particular image. And descriptor, what it does is whatever key points has been identified, it could be using any method, whatever key points have been identified, it takes it and then tries to describe the neighborhood, or forms a description of the neighborhood. Okay, so I'll go to the descriptor, Sift descriptor over here. Now, let's say you have the information of the key points. What the Sift descriptor does is it will divide the particular. It will take the neighborhood, right? It will divide the particular image into grids and subgrids and so on. Okay, so once you have a subgrid, okay, subgrid would be a small representation of the whole image. Okay, so it is basically looking at the neighborhood of each key point. Now once you have a subgrid, it takes the gradient, okay, of that particular subgrid, right? And once you have the gradient, you have the information of the orientations, so it will create a histogram of the oriented gradients. Okay, and once you have all the histograms, the HOG features over here, it will then normalize it. Okay, there is a two-stage normalization that happens, and finally what you have is the Sift descriptor. Okay, so what you see here is, I'll just repeat once again. You look at the neighborhood, so that is in the form of a grid. You divide that into subgrid so that you form small patches around the key points. Now, from there you find what is the gradient, right? So you have the magnitude as well as the orientation information. You calculate the HOG from that. So that means what you're doing is you're finding the histogram based on the orientations which are obtained from the gradient, and then you concatenate them together and normalize them. Okay, and one difference over here again is in this case, when you're trying to find the histogram, right, you use 36 bins over here. So for 0 to 360 degree, as I'll show over here, when you have 0 to 360, okay, you just calculate that, or take it into 36. You take 36 bins, okay, for representing the whole of 0 to 360 degree as an example, and then normalize them. Okay, so here this particular descriptor just gives a better information over here. So I'll just explain once again. What you do here is you have the particular key point, right? And let's say this is a particular image that we are considering. Okay, so here the gradient operation has already been done and you have the orientation information throughout the image. Now what you do is you can take each neighborhood regions or each different patches. So in each and every patches you see that there are different orientation information, right? You calculate the HOG of that, right? So instead of using the whole histogram bins, you can quantize that or reduce the number of bins over here. In this particular image or in this particular example, they have considered an 8-bin histogram. And once you have that, the peak of these histogram will give you what is the dominant direction, right? So now these directions or the orientations are represented for this particular image patch, okay, or this particular key point neighborhood. You have this particular histogram representation, and then all those are concatenated together. So this is just a representation of this particular image, okay, with the HOG representations shown in an image form, right? So what you do is, as I said earlier, once you have the gradient orientations present, okay, after calculating the HOG, you concatenate them together and then you do a two-stage normalization. So why normalization is done is there may be illumination variations which is present in the output, okay, or the information or the histograms that you have. So in order to make it invariant to the illumination variations, you kind of just normalize the vectors, okay. So first a normalization is done, followed by thresholding, and then again a renormalization is done, and finally what you have would be a feature vector, okay, which is basically the normalized HOG vectors, okay, and that is what you call as a Sift descriptor. So what a Sift descriptor does is how it's different from that of a Sift key point detector is once you have the key points, it will look at the orientations present across the neighborhood of those particular key points, and then these orientations are represented in the form of a histogram. By calculating the HOG features, they are concatenated together and normalized, and what you get would be the the Sift descriptor. Okay, so instead of this Sift descriptor, there can be, as I said, mix and match between different types of detectors and descriptors which have been experimented on different applications. Okay, so just to show you an example of how it looks like. So this is the image of a building which was shown in one of the previous slides. So in this particular image, this is an example of how the Sift helps with identifying key points. So what we see is that the key points have been detected at the edges, the corners which are present in the image. Okay, now once the key points have been identified, you can use the Sift descriptor, okay, in order to point out or in order to describe the neighborhood. So basically the orientation of the gradients of each of these key points have been shown over here. So these orientations helps to give us an idea of how the edges are present in the particular image, and the dominant what directions which are pointed out by the histogram orientations are the ones that we consider for further describing the image further, or for, let's say, detecting an edge or detecting the corners, etc. So this is an example where the orientations are overlaid on the original image. Okay, if you have any doubts till now, I'll take questions before going further. Okay, I'll go further with texture. So, as I said in the beginning of the lecture, there are different ways by which you can represent an image. It could be with the help of key points, or it could be with the help of finding texture in a particular image, or you can transform the image to some other feature space in order to better represent that image. Now we will discuss about how the images, or what you mean by texture in an image, and how exactly it helps with representing an image. Now here in this slide, what you see are some images, okay, where texture plays a very important role. So we see that there are images of leaves, there is an image of a grass, there are images of bricks and a stone. So if you look at these images, what we see is uh, the particular region of interest has got a certain form of texture, okay, which is kind of repetitive, or you can make out a certain pattern, okay, of the different intensity variations in the particular image. So when we look at the image, we can easily say that this is an image of a brick, okay, or that, you know, these are some leaves which are present, or these are some leaves, right? So how the humans are able to identify that, it is basically by recognizing what is the patterns or the texture which is present in the image. So you can say that texture is kind of a repetitive pattern of the changes of intensity across a particular image or object of interest. Need not be for the whole image, it could be within a particular object also. Now, by identifying this particular pattern, it helps with various applications of computer vision or image processing. So it could be applications like, for example, trying to recognize or identify certain objects with respect to the others, or even if you're looking at simply texture images with just the texture alone, it helps us to identify or differentiate between two different textures, okay. And further, you can also use once you have the texture information, or you are able to represent the image in the form of its texture, you may be able to perform various tasks. Like, for example, you can do a texture synthesis, that is, you can try to synthesize or generate new images which has kind of the same texture as the sample images that we have, okay, and so on. So there are various applications of these texture information which is present in the image. So basically what texture means is, as you find or as you see in these images, it is kind of a repetitive pattern that can be that stands out in that particular object of interest. And there are various ways by which you can try to represent the image in the form of its texture. Okay, so some of the forms of representation is the local texture representation, where you try to take an image, okay, and let's say you are forming, or you're taking patches of an image, or you're taking small blocks within the image, and you try to find out the texture of each of these image patches. Okay, so you have an image, you have different patches, and you try to find out the local texture representation of each of the image patches. Okay, that's what you call as a local texture representation. Then you have the pooled texture representation. So what it does is, it will just take an image, okay, with just one patch of the image, and try to recognize what is the texture in that patch of image alone. Okay, so it is a patch within an image where that particular texture alone is described. So we won't be looking at pool texture representations further. We'll be concentrating on local texture representation, as well as data-driven texture representation. So what data-driven texture means is, the data which we have is a sample texture patch or a sample texture image, out of which you can synthesize further or new textures. Okay, so that is what you call as data driven texture representations. An application is texture synthesis. Okay, now to understand the concept of using texture as a template, okay, and also to understand how the correlation works, you can consider, like, for example, let's say I have an original image. This is the original image, and this is a template image that I have. Okay, now this template image has been taken from one of, oh, it is actually belongs to one of the patches which is present in the original image. Let's say it is this particular region over here, right? Now what I'm doing is, if this template, if I'm trying to do a convolution of this kernel, I'm taking this particular sub patch or image patch as the template or the kernel or the mask, and I'm trying to convolve that with the original image. What happens is, it basically does a correlation operation where it will give a high value wherever this particular patch has a it exactly matches with that of the original image. And if it does not match exactly as that of the original image, then it gives a low value. So after doing that particular convolution operation, the output image looks like this. So in this image, what we see is there are certain regions where you have high intensity values. So if I look at this particular point over here, it has got the highest intensity value, right? So that means this patch has perfectly matched at the corresponding. So here means it is somewhere here, I guess. Okay, it has perfectly matched with that particular location, and that is why it has a high value. And wherever, so depending upon how similar the template is with respect to the underlying image, you have varying degrees of intensity values, right? So here in these regions you find that the intensity values are less, or in these regions it is less, okay, which says that the template under consideration, or the kernel that we are considering, is not exactly matching with that of the underlying image. Okay, so this particular technique can also be called as a template matching, okay, where this kernel or mask can be considered as the template, and it can be used for operations where you're trying to detect the presence, or you're trying to recognize the presence of a particular pattern in an image. So let's say you have an image and you're trying to identify a certain pattern within that particular image. That pattern can be used as the filter mask or the template, and then you can try to do this correlation operation in order to find out where exactly that pattern is present within the image. So once wherever you have the high intensity values, that means it is exactly matching, and depending upon how or the degree or the level of the intensity values in the output image, you can say how similar or how different it is from the underlying image. So just introducing the concept of template matching. Now coming to quantitative texture measures. Now there are various feature extraction techniques which can be used in order to identify or in order to find the texture of an image. Okay, so what it does is, now these different techniques would look at the intensity values of the neighborhoods in different ways, and tries to find out, or it tries to measure and quantitatively measure that in different ways. Like for example, I'll just list out some of the features which may be useful for you in future also when you're going with computer vision applications or projects. Like for example, the simplest feature or texture feature which you can think of is the histogram features. So histogram, as you know, it is just taking the histogram of the image pixels which are present in an image, right? Now, once you have the histogram, you can look at the histogram and calculate what is the mean or the standard deviation or the skew, etc., of the histogram. Okay, and these measures can be used as a feature vector to represent that particular image. Okay, and that is called as histogram features. Now histogram features is one of the very simplest techniques by which you can identify, or you can try to represent the image. But one one problem or one limitation of the histogram is that even though it helps to find out the how the pixel intensities varies within a particular image or between two different images, you'll be able to find out how different the images are. Still, there may be images. If you remember, in the previous class, we had seen two similar looking images. Okay, one of that of a zebra and one of that of a dog, where they have the almost the equal distribution of black and white pixels. Okay, and the background pixels also had somewhat the same intensity value. So there may be two different looking images, okay, which may have the same kind of histogram distribution. So that is one disadvantage, which means that it will look at only the pixel value variations within the image. It does not look at the location of the pixel intensities. Okay, and that is one disadvantage of histogram features. So better texture features where it looks at not just the intensity values but also the spatial locations, or it also considers where exactly the texture features are located. Okay, those would be better features, and one such example is the co-occurrence matrix, as is written over here. It is also called as the gray level co-occurrence matrix, and the it is abbreviated as GLCM. Okay, now we will see about GLCM in detail in the later slides. So what GLCM does is, as it says, co-occurrence. It looks at two pixel intensity values, and it will identify all regions, okay, in various directions, all regions where these two pixel intensity values occurs as pairs within the particular image. Okay, so that is what you call as co-occurrence, how where all it occurs together as pairs within the particular image. So that is how we calculate GLCM. Then you have other features like GLRLM. GLRLM stands for Gray Level Run Length Matrix. Now, how GLRLM is different is it will look at how many pixel values are present with the same intensity value, okay, along a particular direction. Okay, so given a particular image, it will look at those pixels having exactly the same intensity value that are adjacent together, that is, it forms a neighborhood or which is adjacent to each other, and it will run along a particular direction. So that is why it's called as a run length matrix. Then you have other features or other texture features like morphological gradients. So so far we have looked at gradients where you just take the finite difference approximation of the regions or of the pixel values. Instead, you can also do a morphological gradient, that is using morphological operators to find the gradient information in a particular image. Okay, and by using morphological gradients also, it helps to identify different structures present in an image. It can be a blob structure, circular kind of objects, or it can be linear objects which are present, or square regions which are present in an image, or so on. Okay, so morphological gradient operations can be used. Now another set of method or another texture method which can be used is by using it's not exactly a texture with spatial information as such, but still we can use a Fourier method, or a better improved method would be a wavelet transform, where you can decompose an image into different scales. Okay, and we can call it as a wavelet decomposition. So basically you look at the wavelet representation of an image, okay, in various directions, and then you can also form just like how you have a Gaussian pyramid, you can also form a wavelet decomposition of different levels, okay, of a particular image, and that is one representation of the texture measure. And another example is the LBP, or it is called as the local binary pattern. So in LBP features, what it does is it will look at a particular center pixel under consideration and looks at its neighborhood pixels, and it will threshold the neighborhood pixels with the value of the center pixel, and that will give you a binary pattern. And this particular neighborhood pixels which have been thresholded, it is from that histogram is calculated, and that is called as the LBP histogram. And from the LBP histogram, you can either try to find out the distance measures between different LBP histograms in an image, or you can find out the LBP histogram features. That is, you can extract one-dimensional features from the LBP histograms or so on. So this was just an overview of the various quantitative texture measures that can be used to quantitatively analyze the texture in an image. So basically what it does is it will look at a center pixel, okay, and also looks at its neighborhood region, and tries to find out the presence of a particular pattern, or like for example, if it's a co-occurrence matrix, it looks at the presence or the occurrence of pixel pairs with certain pixel intensity values. So further what we'll do is in the next lecture class onwards, we'll just have a look at what how exactly co-occurrence matrix works, the GLCM texture analysis method, which was one of the most popular methods earlier. But right now, since you have machine learning or deep learning algorithms coming, you do not go further, and you also have other more advanced techniques. But still, GLCM is a very important concept to know about. So we'll be going through the GLCM concept, and then we'll also see how texture images can be synthesized, or texture synthesis techniques. Okay. So if you have any doubts, I'll take your doubts now. Okay, I'll upload today's material in the Teams, and you can go through the material. If you have any doubts, you can ask that, and also you can go through the reference text materials which are given in the course plan. And apart from that, for these first few lecture classes on the basics of the computer vision, and on spatial filters, and the texture methods and so on, you can also refer Gonzalez. It's an image processing textbook by Gonzalez. You can refer that also, just for the initial few topics. And then when we go with after texture synthesis, we'll be going to the introduction to a fine geometry, and then we'll continue with image registration, where you can apply each of these affine and Euclidean geometry or transformations for different kinds of image registrations. Okay, if there are no doubts, I'll end the meeting. I've taken the attendance. Thank you.
Thank you, ma'am.